Hi, one of the issues when it comes time to applying these stress transformation equations for the state of plane stress is how to deal with the signs. And we got three different signs that we have to be looking at. One associated with the normal stress, one associated with the shear stress, and one also associated with the angles that are involved. Let's take them one at a time. The normal stress is pretty easy, and that is that in these equations, we almost always will say that tension going away from the plane is a positive, right? So that's usually not too bad. The shear stress is a tricky one, and we'll come back to that in a moment, but right now you see the positive shear stress on the x outward normal plane. Ugh. See, it already starts to get complicated just in talking about, well, what's the basis or reference. But for right now, we'll come back to it. We've got here on this x outward normal in the positive x direction that we've got this shear stress acting up. And that can be confusing, so we'll come back to it. And then the other item is, what do we do? How do we deal with the angles? So let's talk about the angles next, and then we'll come back and apply these into the stress transformation equations to help illustrate how this all works. All right, so when it comes to angles, here we'll go back to our basic state of stress that's represented by the basic stress block. Right now, what I find very useful and handy is to have a little post-it around. This is a nice brightly colored one, which I also encourage, but any color post-it usually works pretty well. And what I also like to do is I like to draw an arrow to this x plane. Now notice the x plane is actually a vertical plane, but it's that positive x outward normal. Think of this post-it as the solid outward goes away from this solid, and that would be our outward normal. And what we're going to do is to go to an angle on an inclined plane is we'll rotate that until it lines up. So over here at this point that I got this plane that is shown at an inclined angle, then I'm going to rotate it counterclockwise. Right? So it's a right-hand rule business, right? And so stick the thumb where the x-axis is, and so to speak, right? And so we're going to rotate that, rotate that this way in a counterclockwise fashion, just like regular geometry or calculus designations. Right? So that's counterclockwise positive is our direction for measuring then our theta. Now, there's a whole lot of tricky elements of this, one of which is that you're going to see people derive equations for any old plane, and they'll sometimes take advantage of, they're not really shortcuts, but there's other ways to represent this. But we're going to go back to this bedrock of, if we measure everything from the positive x-axis, this horizontal axis, and then measure everything from there, we'll be golden no matter what. And then over time, as you get comfortable with that, you'll begin to see what these so-called shortcuts are really doing, what they're all about. All right, so again, counterclockwise positive from the x-axis. All right, so let's see how that plays out for 4 different planes, and which turn out to be at 90 degrees to each other. So let's take this first one. Here's our rotated stress block. It looks like this now. It's inclined, and we're going to rotate, find that x-axis going to the right, and we'll rotate it to the normal on the plane, the outward normal on that plane. Right? And that would be a small angle the way I've got it shown here. It looks like about 45 degrees. And so, boom, that would be your plus 45 degrees. Now, if we want to go to this next plane, what we're going to do is we're going to rotate, again, starting from the x-axis, and rotate it, a lot more, right? We're not lining up with the plane. We got to line up with the normal to that plane. And of course, compared to this first one, that's another 90 degrees. So if that one's 45, this is a plus 135. Right, adding the 90 degrees to it. We come to this one down here, right, start this way and go positive all the way around, right? So if this is 45, then that one becomes 135. 135 plus 90, this would be 225 to get to this one, right? Now, you could have, if you wanted to, have gone the other direction. It would be a smaller angle, and it would be negative. Right? So you can get there either way. It just changes the number of positive. Negative positives is counterclockwise from the x-axis, and negative would be clockwise from that. Come down to this last one, and here, note, you got to go all the way around to get the positive angle, or you could have done a small angle, but that would have been negative, right? And so people like to do oftentimes a smaller one. Doesn't really matter. You just have to have the correct number, whether it's positive or negative, and to use in our expressions. So let's see how this plays out a little bit when it comes to the normal stress on an arbitrary inclined plane, right? Sigma n, the normal stress on that particular arbitrary plane, right? The first term is the average term between the normal stress on the x-plane and the normal stress on the y-plane. That's the first term. The second term is the difference between those two, and then divided by 2 times cosine of 2 theta, and then the third term is plus t, the shear stress term times sine of 2 theta. Couple of things to remind you about. In this cosine and the sine term, it is twice the angle that is there. And that was all because, if you remember in our derivation, we had a sine squared, a cosine squared term show up, and we had a sine times cosine term of the same argument. And we simplified those down with the half angle / double angle definitions. And that's how we got to this more simpler version that we see here, and why that 2 shows up. So let's take a look here. Let's do something really simple. If we go from this x outward normal axis, the positive x outward normal, over to the positive y normal, so going from here to there, then we should get in this expression not sigma x out of all this thing, we should get sigma y. So let's see if that works out. Right now, if we go from here as our reference, that's our datum, and go this way, we've rotated 90 degrees. So theta is a plus 90 degrees from here to here. Right? So in this term, of course, that doesn't change anything. This term, cosine of 2 times a plus 90, well, that's a cosine of a plus 180. Right? And cosine of 180 is minus 1. So this whole term will end up with a minus sign right here. Hold on to that thought. We'll come back to it. And tau xy of sine of 180 is going to be 0. So that term is going to go away. Right? So that means if this one became a minus 1 and this was basically a plus 1, notice what happens. That minus means here that sigma x over 2 will subtract off of sigma x over 2. That goes away. We have sigma y over 2 minus a minus sigma y over 2. In other words, we're right back to then the sigma y value, right? Which is what those expressions should tell us. And it will turn out, it turned out it was positive, right? So if we started off with a positive stress there, we ended back up as we went from here to here in that expression, right? Right? If we go all the way over, notice what's going to happen, right? Starting from all over at theta equal to 0, and we go all the way over, that means that we're going to have positive being outwards, right? Tension. Theta would be all the way around, that's 180. In the equation, that's going to be multiplied by 2, so 360 degrees. So that'll be 1, that'll be 0, and out of that, we're just going to get sigma x again. And it will be in tension, so it's going out. If we want to get that fourth plane, then what we're going to do, of course, is go all the way. Oh, my arm doesn't rotate that way, so instead I'll rotate it this way. That would be a negative 90, right? Which will become a minus 180 there, a minus 180 here. This term goes away. We get the same thing that we get. The cosine of that angle is minus 1. We'll get the same thing that we did the first time with that y plane, and it's going to be this time directed downwards in tension away from the solid part. Okay, so that's how that would work for the normal stresses, and applying it, going from here all the way around, gets us exactly what we would expect and want to have happen on here. And that's how we interpret the sign that comes out of Elvis. Remember, for the assignment of the positive or negative for our normal stresses to begin with, these two has got to be tension is positive. If either one of those or both are in compression, then that numerical value becomes negative. in these equations. All right, now let's dive in more at the shear stress, because this gets a little bit more confusing. And this is where your right hand is going to be particularly important, and your thumb and your forefinger are particularly crucial. Right, now you can decide if you want your index finger to be the normal or if you want your thumb to be the normal. Either one, it doesn't really matter. I'm going to start with the thumb being the outward normal. And so the index finger points in the positive shear direction. Right? So we'll start with taw xy. Right? Now, as we rotate to this plane like we did last time, here on this one, notice that we're initially set up like this, right? The little gun-like thing, right? When we were kids, that was the imaginary pea shooter, right? So you got the thumb outward, and you got the index finger is the direction for this little one right here. Now note what's going to happen. That's a positive 90, right? So when we come into here, we've got sine of 2 times 90 is now sine of 180, which is 0. So this whole term is going to go away. This one, cosine of 2 times 90, that's cosine of 180. And, oh, wait a minute, cosine of 180 is a negative 1. So this whole expression, taw nt, will equal the opposite of taw xy. So come back, rotate, and then that negative value means we've got to turn that around, and physically then that shear stress on that plane is going the other direction. And technically that is taw yx. Remember, the subscript actually tell us something, that y is the plane that we're talking about, right? That's this one right here. X then is the other orthogonal component. Yeah, there is taw xz, and there's also taw yz and zy and zx, right, in 3D. Right, so that's why we get a little picky about the meaning of the order of those subscripts. But this is actually physically, it's technically taw yx. Notice back in this expression when we did that, the absolute value of those two is identical. That minus sign that showed up just got this oriented and flipped into the right direction, because remember what has to happen here is in order for this to be in equilibrium, right, we integrate that shear stress over that area, and that means that we've got to have something that equilibrates that on the other side. It's because the areas are the same on both sides of that little differential element. That will also be taw xy. Same thing here on the other side, and it has to go in the other direction to work. If you do the angle parts all the way around, it'll work out, right? You'll get to this side, theta would be 180, 2 times 180, 360, right? And so you do, gotta get this right, here we go, boom, take that all the way around, boom, this one is pointing downwards. When you do the other one, it's gonna be, well, that one's hard to do with your hands, but notice, boom, and then we flip it with that sign to the other way around. Same thing, it all works. These shear stresses always have to point to each other on the corner, or they have to go away from each other on the other corner. Kitty corner, catty corner, whichever phrase you like there. Those shear stresses always have to pinch that diagonal in one of the two directions. These are the two sets of now positive stresses, both normal and shear, on the x outward plane and the y outward plane in their two opposite opposing planes.